All right, well, first of all, I would like to thank everyone at C&e News for putting together this great event. I'm very honored to be here. So today I will share with you a little bit about my journey through the field of supramolecular chemistry, but also some of the work that my group is doing in developing squaramide-based supramolecular polymers for applications in the biomedical area. So as I was preparing for my talk today, I was sitting across from my daughter who was playing with one of her most recent toys, the strawbees. Strawbees are connector pieces and drinking straws that you can fit together in order to build objects with varied complexity, but as well with function. So you can build, for example, bridges that can sustain more than their weight, and you can also build objects that open and close, such as this umbrella shown here. We can think of supramolecular chemistry in an analogous way. If, for example, we now change out the drinking straws and the connector pieces for molecules, and we bring them together using non-covalent interactions. And we can bring them together such that we can make both discrete structures, but as well polymeric architectures. And what is common to these two particular structures is that both of them can show emergent properties and functions when they are self-assembled. And so, for example, if we're talking about a particular polymer, the polymer can show, for example, mechanical properties or bioactive properties that are not seen in the individual monomers. So how did supramolecular chemistry start out for me? Supramolecular chemistry started out for me at the end of my undergrad at the University of Toronto. And this is where I got exposed as an inorganic chemist to the field of metallo-supramolecular chemistry. And I was really attracted to the high degree of symmetry and as well intricacy of the various complexes. But something as a synthetic chemist that stuck with me was that you could make these very intricate structures in very few synthetic steps. So this led me to pursue looking for a PhD in supramolecular chemistry, and this is how I ended up at the group of Hannadi Sleiman at McGill University in Canada. And well, in her group, what I did was I developed both monometallic platinum-based complexes and as well supramolecular complexes to target the guanine quadruplex as an anti-cancer strategy. But what was really important about this experience was that I was able to interact with both computational chemists and biologists, which very much stuck with me in how I do research today, but also I realized that I really enjoyed working at this interface of chemistry and biology. So, close to the end of my PhD, I read a paper of Bert Meyers on supramolecular polymers, and I decided that I wanted to change directions a bit in my research. And so this is what brought me over to the Netherlands in his group at the Eindhoven University of Technology. And it was in his group that I was studying, or I was exploring actually, how we could bring these supramolecular polymer materials based on these uridoperimidinone units into the biomedical area. So I explored strategies to modulate their mechanical properties by mixing various monomer species or supramolecular monomers, and as well looking at how to introduce bioactivity through the tethering of peptide moieties. And it was after this stage that I became only more curious in how far we could push these materials in order to really instruct cellular behavior. So this is what brought me towards starting my independent career at Leiden University. And in my research group, we are very interested in how we can borrow ideas from nature, in how nature is able to construct very complex structures, starting from molecular building blocks from the bottom up. And these structures can also have function. And in addition to this, also how cells, or how we can mimic some of the attributes of these materials in their capacity to stimulate cellular behavior. And we would really like to use these particular materials in areas such as cell culture, in the preparation of both complex tissues and tissue and disease models, in the areas of regenerative medicine, more specifically for cell delivery, and in the area of drug delivery. So I would really like to focus on one particular area that we're working on, and that's in the development of materials for 3D cell culture today. So if I was to ask this group of people what they would like for lunch today, this group of people would say different things, surely. Some would like pasta, others would maybe like tacos, And some might like butter chicken, but because we are in summer, others might like barbecue. But if this same group of people were to be affected by a particular disease, most likely this same group of people would be treated by a particular drug, and most likely the same drug. However, we now know that this model doesn't necessarily work, and that's because of the genetic makeup of the people in this group is most likely, or is different. And one area that looks forward to change how we perform medicine, but also in how we search for new drug candidates, and as well how we understand disease, is the induced pluripotent stem cell field. And induced pluripotent stem cells are essentially somatic cells that can be taken from a patient in a laboratory setting and are reprogrammed into their pluripotent state. And then these cells can be then differentiated through using certain biochemical and as well chemical factors into the necessary cell types, such that one can perform various, let's say, or explore various applications in disease modeling, in drug screening, and as well drug discovery, and as well in toxicity testing of various drug candidates. But another area where these cells can be used in is in the area of cell therapy, where, for example, one can start to think of repairing or regenerating any tissue of interest. So although there has been tremendous progress in this field over the past 10 years, or just over a decade, since the groups of Yamanaka and Thompson have discovered these particular cells, there are still problems related to both their production and as well as their application. And in our research group, we are interested to see, or what we would like to do is use a supramolecular biomaterials approach to overcome some of the challenges in the production and application of these cells, and as well of their differentiated derivatives. So if we are to think about the natural, if we're to think of a material that should support these particular cells, we should think of the natural material by which all cells reside in, and that's the natural extracellular matrix. The extracellular matrix is a complex composition of both soluble and as well insoluble proteins, and it provides not only the structural support for these cells, but also a water-rich environment with specific bioactive cues to direct their growth. And so one particular synthetic material that has had great success in this regard in mimicking this natural environment is the hydrogel. And hydrogels are composed of either chemically cross-linked or physically cross-linked polymers, and these polymers can be outfitted with various bioactive cues. And in my research group, we are interested in using specifically supramolecular hydrogels because of their non-covalent character, which endows them with unique properties such as modularity, tunability, responsiveness, dynamic character, and when we outfit them with bioactive cues, potentially biomimetic character. So in order to construct such polymers, we need a monomer, and that monomer should have some sort of directional interactions in order to propagate the growth of these polymers. And the particular directional interaction that we're interested in is in the hydrogen bond, and for this is where it brought us to the squaramide moiety. So we use squaramides because they are structurally simple ditopic synthons, and these can associate with one another through hydrogen bonding at both ends of the molecule, or at both ends of the synthon. And when we insert this into the hydrophobic core of a bol-amphiphilic monomer, we can direct the growth of polymeric structures, and these polymeric structures can have lengths on the nanoscale. On the nanoscale. These particular monomers, although they form nano objects several hundreds of nanometers in length, they do not form gel phase materials. So what we did was we took this squaramide unit and then inserted this into a tripodal monomer, and also explored the hydrophilic and as well hydrophobic balance in order to be able to construct these types of fibrillar architectures. So when we found the correct balance, we were able to obtain gel phase materials, and these gel phase materials are mechanically soft in character, similar to the properties that are observed in the embryonic environment, but also they show self-recovery properties. So what we did is we took the self-recovering character of this particular material and we pipetted it with a single-cell suspension of induced pluripotent stem cells. And what we found is that when mixing these two together, we could easily see the cells within this material, but then also these cells showed their expected behavior after 24 hours in culture. So they form very compact aggregates, which are typical for this cell type. And then in the second step, what we did is because we wanted to see if we could release the cells so that we could perform downstream analysis. And this was possible with this particular gel because of its supramolecular nature. And this is just a flow-activated cell sorting experiment where we show that the cells do retain their pluripotent character. And this is similar to the typical methods by which these cells are expended in a 2D culture setup on vitronectin. So where to for these materials? We've shown that they are cytocompatible. We can easily see cells in them. We can also release the cells, and they do retain their pluripotent character. So if we think of the processes of both of development, more specifically in terms of cellular development of a particular cell subtype or a particular cell type, and also in the self-organization of tissues, what is very much necessary is that there is this really concerted action of both biochemical and biophysical cues that are presented at both the right place and the right time. And well, so where does that leave our materials and where do we need to go with them? Well, the next steps, we have to see how to modulate their mechanical properties. How stiff will we need to go? Well, that will depend on the target. And what types of bioactive units will we need in these particular materials? And once we have these bioactive units, how dynamic will they need to be? And as well, will they need to be responsive? So with this, I would like to thank my research group over the years. It's been a really fun experience to work together, but also I am extremely proud of their accomplishments. I would also like to thank the larger group with which my group is embedded in, which is the Supramolecular and Biomaterials Chemistry group at the University of Leiden. And I would like to also thank all my collaborators over the years, the funding sources, as well as I would like to make a couple of special mentions to both my family for their support over all of these years, and as well being the very first funders of my work. And also I would like to especially thank my husband, Pablo Englebien. He has been a long-time computational collaborator in many projects, and as well for being a collaborator at home. And I would like to thank all of you for your attention.